Ready, Amanda?
Yeah. I'm waiting.
Oh.
That is ready.
Ready, Grace?
Yes.
Okay. So, we're having a look. Newton's law. Not like you've seen this before. So, remember this?
Why?
Yeah?
Is it hard?
Oh, it's actually not.
I've never seen it.
No, never seen this before. As you know, the Earth pulls on other masses to it, and the Sun pulls on the planets such as the Earth. Therefore, there must be some field, like an electric field or a magnetic field, around the Earth. Let us suppose that the field around the Earth is a gravitational field. It would look like this below. So Sohi, what happened yesterday was we accidentally did some of this lesson. I skipped the last lesson. So I think these students here, maybe you already drew this picture?
No, I threw it out.
You threw it out? Wow. Okay, so this is the field around the Earth, and the masses get pulled into the Earth. And as I was saying to Hareen yesterday as well, that there's a field around everything. So you can't see it, but the gravity field is pulling everything together. But it's very, very weak. So for small things, we don't see it. But for big things, like the Earth, we can see it. So this here, these are the field lines. And then what are these circles called? Do you remember the name for these?
Field.
No, these ones are the field.
Oh.
And the circles?
The co-potential and
Equipotential.
yeah.
Remember this word from electric fields? Yeah. Okay, so if you can draw this gravitational field.
Did you see gravity force?
Gravity force?
No.
No, I didn't.
From Disney.
G4.
Yeah.
G-force?
The one with what are the journals?
I have no idea what you're talking about. This doesn't sound...
Kinetics. That's kinetics.
Wow, okay, no.
I can show you a picture.
Sounds terrible.
No.
No?
It's interesting.
Sure. Okay, continue. You got this picture, Sophie?
At first, I think it's for kids to look at, but at last, no, not for kids at all.
For adults.
Yes.
Continue?
Mm-hmm.
Yep. It was discovered by Newton that masses attract other masses, and that the bigger the mass, the more force there is. And again, I think you wrote this formula down yesterday, but if you threw it out, here's the formula again. So that's the formula again. Why did you throw it out?
Because it's ugly inside.
Okay, fine.
Force.
So what happens if the masses get bigger? Do you have more gravity force or less gravity force? More gravity force. And if the distance gets bigger between them? Less. And just be careful, that or is the distance between the centers. Yeah. So Newton was a busy man. He has many laws. This is his gravity law.
What is G?
G is a constant. It's always 6.67 10 to the minus 11.
Just write down F and G.
F and G?
And formula of F and number of G. G equals 6.6.
Oh yes. And the units.
Yes.
Yeah. Yeah. Okay, continue. Grace? Yeah. Now this is the part in the lesson yesterday where I noticed, wait a second, I skipped something. So, notice how similar this is to Coulomb's law. So, before I actually go ahead, if you compare the situation, we have maybe like a mass here, and a mass here, and then we might have a charge here, and a charge here, and there's a force, and there's a force, and of course there's a force this way, and there's a force this way. Here, this F is equal to G N M over R squared, and it moves around. And here, F equals K, Q over R squared. Can you see how the formulas are very similar? Yeah? Charges. Small charge and a big charge. So the small charge will move around the big charge. Yeah, and big mass and small mass. Yeah, like Earth and Moon. Proton and electron. You know, from chemistry. Can you see how they're actually nearly the same? But the big difference here is G is 6.67 times 10 to the minus 11, and here K is 8.99 times 10 to the 9. If you compare the difference, that's like a 10 to the 20 difference. It's a huge difference. So my point is, this force is much, much, much stronger than this force. That the force between charges is stronger than the force between masses. You don't, no wait, you don't need to write this down. This is just to, or you can if you want, this is just to get you thinking about things. Let me give you an example. Have you ever stuck a little fridge magnet, or a magnet, for example? Let's say we take a magnet. This, yeah.
What is the force between the ends?
These ones?
Oh.
Gravity. You know, when you have two magnets, they're very, very hard to pull. But if you look at my phone, what's pulling my phone up? My hand. And what's pulling it down?
Gravity.
Of the whole planet Earth. So me versus planet Earth, who's winning?
You.
I'm winning, okay. No, because I can move it up. You know? Now, if the Earth was a magnet, and this was another magnet, I would not be able to pull it. It will just go straight down. So I'm just trying to say that gravity is very weak.
But Earth is like a magnet, right? Has magnetic.
Yeah, just like it's a very small magnet inside it, yeah. This here is called a gravity force, and this one here is called electrostatic. Is very strong. Electrostatic force, I should say. Okay. So, if you remember when we had electric field, we had electric field strength. Does anyone remember the formula? You had a field and you had a charge in the field. Does anyone remember the formula for the strength? Oh no. F over Q. Remember this now? Are you sure? Because then you say F equals QE. So the electric field strength is force per charge. So what do you think the gravity field strength is? You know what? You are right. It is force per mass. So here its unit was newtons per coulomb, whereas here its unit will be newtons per kilogram.
What's that E again?
Electric field strength. Electrostatic force.
Electrostatic.
One word. Okay. Let me go just back here a sec. Can I scroll down? Yeah. Okay. Let's take an example. Here is our physics student. And they have a mass here, M. And you know there is a gravity field pulling down on the mass. Let's calculate the field strength. Okay, the field strength. The gravity field strength. I'll just write for the moment. Yeah, gravity field strength for the moment. Okay. So the formula is F over M. This is the M here. But from Newton's law, the F is G, let's call the Earth is big M, okay? G M over R squared. That's divided by M, the M here, okay? So that will be G M over R squared. Yeah? But you might say, well, there's another way you could have said it. You could have just said gravity field strength equals F over M. So that means F equals gravity field strength multiplied by M. If I just bring the M up here. But do you know there's another formula for this here? What's this called? This is called the weight, isn't it? So what's another formula for weight? mg. So if you compare here, what do you get? Yeah, the m's cancel. So you can think, oh, that's interesting. The g, which you have as 9.81 meters per second squared, that is the same as how strong the field is, 9.81 newtons per kilogram. In other words, this g here has two jobs. It tells us the acceleration and it tells us the field strength. Now this here is only true on Earth. It's not true on the moon or another planet. So we want a formula to calculate it. Well, we got this formula earlier, so we can say that this equals G. So anyways, after all of this, all I'm trying to do is get to the formula, and this is the formula. The gravitational field strength is equal to Gm over r squared, and this will equal 9.81 newtons per kilogram on Earth. And you can check it. If you put in the G and the M for Earth and the radius for Earth, you do get this number. Zoom out. You don't need this. This is the proof of the formula. Now, if you really think about it, this makes a lot of sense, which I'll explain in a moment. Continue. Yes? Okay. Let's think about this. If you remember, for example, here is our proton, and here is our field. So if you remember the formula for the force, that was equal to E multiplied by the charge, which are called Q. And then if we look at the Earth, for example, here's a mass here. I'll just put this. And here's the gravity here, gravity field. What's the formula for the force here? That is equal to, actually let me just write this a bit differently. I wrote EQ, I should write, Q multiplied by E, and here the force is M multiplied by G. So if you notice that this is the field strength, and what's this one here? The gravity field strength. And what's this? This is the mass of the particle, and this here is the charge of the particle. And the potential energy here is M G H, and the potential energy here is Q E and H as well, or D if you want to call the height here D, and here the height here is H. You see, what I'm trying to do is to show you that this topic in physics, which we're doing today, it matches what we have been doing. You can see they're similar. And for example, in this topic, if you have a Q1 and a Q2, what's the force? That's K Q1 Q2 over R squared. And here, if you had an M1 and an M2, what's the force? It's G M1 M2 over R squared. Can you see how the two are actually nearly the same? But there's one big difference which I want to show you. What happens if I put an electron here? Will it move up or down? And let me help you out here. This is positive and this is negative. So which way will the electron move? It'll move up. Can you put a mass here that will fall up? No. So this is the big difference between the two. Here you can have a positive charge and a negative charge. Here you can have only a positive mass. Can you have a negative mass? No. Be cool if you could, but we don't have negative masses. Now the reason I'm telling you this, can I scroll down? Yes? No.
You have to write this down.
No, you don't have to. You don't have to. As long as you appreciate what I'm trying to do. Can I go down? Oh, Amanda. Are we just waiting for... No, okay, I guess not. So, 2 hot dogs. 1 hot dog. 1 hot dog. 2 sausages. Bacon. Yeah, I'm not surprised. Oh, what did you get? Family bucket? No. Small mega box. Not kilo box? Gigabox? No.
The name is
Mega box? Maybe you need a milli box. Micro box? Okay, can I go down now? Yes. Okay, continue. So the reason I'm telling you this is because sometimes in the exam students get this question and they freak out. They say, okay, here's a positive plate, here's a negative plate, here's a proton, and the proton is fired and it goes like this, and they want to know how far does it go, and then they think, oh my goodness, I have no idea how to do this. But then if they remember, well, here is the proton, what's the force down here? That's QE. And if they think about a projectile, what's the force down here? mg. So a lot of people don't realize it's actually the same type of problem. That this one here you do as UVATS. The only thing is you have to find out what the acceleration is. So you could say F equals QE. What's the formula for F? MA equals QE. So then the A acceleration to use here, going down, would be QE over M. Then once you know this, it's exactly like a projectiles problem. Because, you know, I give you the angle, I give you the velocity. You don't need to write this down. But do you see what I mean? How fields, you know, some of the questions are familiar. Okay. Continue. That's okay. I was hoping to get 2 topics done today, but I don't think I'll rush it. Yeah, I think so. Okay. No?
I like coffee from little bird.
Yeah, it's good.
Yeah, tastes like coffee.
Oh, that's good. How much though?
2
Cappuccino?
Americano.
Mm. Sounds expensive. I have no money. Yeah. 250? Already, Amanda?
Yes.
Yep. Right, so gravitational field strength G is the amount of gravitational force per unit mass. Mathematically, G equals F over m, like Hareen said. Although we have a formula for F, don't we? It's the Newton's one. So if we put that in, we can get this formula for G. You have this already written down, but if you want to just put boxes around these two formulas, there are important formulas. Yeah? Okay.
No. Only try the formula, not the word.
Okay. Continue. Yes, Hareen?
Wait, what is larger?
Like you usually have a big mass like Earth, Sun, planet, you know.
Bigger, smaller?
Yeah, usually I use big M for big mass and small m for small mass. Okay, continue. Yeah. Right, so let's just recap, summarize. You don't have to write this down, we're just taking a recap. All masses produce a gravitational field which attract other masses. The force between m and m is found by using this formula, F equals G mm over r squared. Fields, or I should say gravity fields, gravitational fields, they always point towards the center of the mass. The field around a small mass can be ignored. So, for example, here there's a small field, but you can ignore it because it's so small. Okay. Because masses are positive, the fields never point out; they only point in. So this only falls down; it never falls up. The strength of the field, you can find it by using this formula. And this is in fact the acceleration also, the 9.81 if you're on Earth. The value of G near the surface of Earth is 9.81 newtons per kilogram. Now you don't have to write this down, but if there's some point in there that you want to write down, you can. Okay? But I think this is just recapping everything we've said. Okay. Anyways, the video, I'll upload it later today, so if you wanted to, copy it down. I didn't upload it yet because I was correcting the September students' heartbreaking physics results, so this is why I didn't do it. And then after I corrected it, I was so sad, and I needed a drink, I needed to relax. It was difficult. And then, of course, Ireland was playing Sweden, and did you see what happened yesterday?
No.
Ireland was winning, and then so it was a hard evening yesterday. It was difficult. Okay, so when one mass m is trapped by another mass, then it will have what potential energy? Positive, negative, or zero?
Negative.
Negative. If it's trapped. Negative. You all know this now, I hope. What's trapped? Who can explain trapped for her?
Great.
What?
What's trapped?
Potential energy the sky, the people falling on the ground.
Yes.
And people lying on the ground is that is
Yeah.
zero, and when it jumps into it,
Yes, beautiful. So he trapped means like if you fall into a hole and you can't get out. So like if this is a hole here, so positive potential energy, zero potential energy, and then if you fall into a hole, you're trapped. Means you have negative potential energy. That if you're down here, you need energy to be free. Trapped means not free. Yeah. So negative potential energy if you're trapped. Yes.
lower than ground.
In the case of the Earth, it means lower than the ground. But in the example of a proton and electron, the electron is trapped because you need energy to ionize, to free the electron. So it's also trapped like this. In the field, yes, yeah. Okay, so just like in the last lesson, we have a formula for the potential energy in a gravity field. Minus GMM over R. Now I want somebody to tell me something that is confusing here. What is this formula for? Potential energy in what? Gravity field. Have you not seen that before?
Yeah, NGH.
Is that MGH?
No.
No. So, what the heck is going on?
When
This
the
is not
orbit-
MGH.
when the orbit does.
Could be. Let me show you. But why don't we use MGH for potential energy? Yep. If it's trapped, yeah.
G is always 9.0.
Yes. This is only for special situations. Yes. This is for when it's trapped. But this is, when do you use this one?
When it's
Normal.
falling.
Normal, when it's on the ground. But I want to prove that these two are the same formula. Watch this. Watch. Yes, it's great. It's great proof. Okay, so let's start here. Here's the ground, and here is the mass here. What's the potential energy here? MGH. And here, on the ground, it's 0 when it's on the ground. So when it falls, what happens? It loses MGH potential energy. Okay? I need to scroll down now. So do you understand, when it goes from here to here, it loses MGH potential energy. Okay. Now, here is the Earth. Here is the mass here, and we'll call this distance R plus H. And then it falls down to R, and we'll call this distance here, well, R. So how much potential energy did it lose using the new formula? Well, on the top it was minus GMM over R plus H squared. And then on the bottom it's minus GMM over R squared.
But it's moving up.
No, sorry, I didn't put it in arrows. This one again also goes down. So it loses, we think, potential energy.
Why do you have to plus the R?
Oh, because the height, this formula,
It's
it's from
from the
the center. Yeah, this formula is the or from the center of the Earth. From the center to center. Okay. Is that okay so far? No, it's not okay. Oh, sorry. No squares here, sorry. The formula doesn't have a square. No. Okay, so this equals GMM over OR minus GMM over OR plus H. Okay? This equals GMM over OR minus GMM over OR 1 plus H over OR. This equals GMM over OR 1 minus 1 over 1 plus H over OR. Okay, continue. This equals GMM over OR 1 minus 1 over 1 minus minus H over OR. You're thinking, where is he going with this?
where's the one? I don't know. What's happening?
I just changed the plus to minus minus.
Oh, I get it.
Okay, now let X equal H over OR. So then this equals GMM over OR 1 minus 1 over 1 minus X. Because, sorry, thank you. X equals minus H over OR.
The one after this is like...
No, but it's fun. Now, let me just go to the left for the moment. Do you remember from GP in math class, you have 1 plus or squared plus or cubed, dot, that equals 1 over 1 minus or. This, if you remember, is S infinity. Do you remember doing this? Yeah. So 1 plus x squared, equals 1 over 1 minus x. Remember this from math class? So, here I can say this is GMM over OR 1 minus 1 plus x squared, dot. Yeah? Now, is x a small number or a big number?
Small number.
It's a very small number because what is the or? The H. The height above the ground. And what is the or?
The core.
The radius of the earth. Yes? So, H is much smaller than or. So it's nearly 0. It's a small number. So if x is really small, then what about x squared? Smaller or bigger?
Smaller.
Smaller. And then x cubed,
Smaller.
smaller again. So because they're so small, we can cancel them and just keep the first one because they're so small. So we can say this is roughly GMM over R 1 minus 1 minus x, which is roughly GMM x over R with a minus in front here. Now, what did I say minus x equals? What's minus x equal to? H over
H over R.
H over R. So this equals m g m over R squared H. Now, do you have a formula with gm over R squared? Have a look at your formulas. Do you have one for gm over R squared?
G.
It's g, isn't it? So this equals m g h. Same formula. Yeah. So anyways, I wanted to show you this because you will see this proof next year as well when you do engineering. It's kind of an important proof in physics that the formula minus GMM over R is the same as the formula MGH, but only if you're near the surface of the Earth. If you're near the Earth surface. Look, I don't know about you, but I think that's pretty cool.
Why is it 1 minus 1 minus x?
The minus
Oh,
1.
Yeah.
Yeah. Yeah. Continue. That was proof. Yes, we did the proof. Okay. Right. Newton's law of gravity is for the force between two masses. This force, the force between masses, is one of the 4 fundamental forces of nature. Oh yeah, we talked about this. And it's another example of an inverse square law. So we talked about this. Also notice the small value of g. That's actually important. Right, so let's see, we have a couple of questions. So let's try this one. What is the force between the Earth and the Moon? And here's some information. So if we can write this one down. How's my battery doing? Yeah, I'm okay.
Before this,
The last slide? Yeah? Oh yeah. Yeah, we talked about, while you're writing this down, let me show you. Can you go back to Newton's law? Yeah. Keep going back. Yeah, here. So this formula here has an R squared in the denominator, and this formula here has an R squared in the denominator. These are examples of what's called inverse square formula, where the distance is in the denominator and it's squared. And these formulas are common in physics. For example, we have it here in gravity and we have it here in proton-electron. But there's other parts of physics that also have formulas like this. So it's a common type of formula. We even did an example yesterday of how bad somebody smells is also like this. Inverse square. It's just vocabulary. There wasn't anything about it. Amanda, I just mean that inverse square is just the name of the formulas that have r squared in the bottom. We call this an inverse square formula. Okay, did you write this down? Right, let's try it. How do I remove this? No, that made it worse. I guess it's stuck. Right, let's just write it down here. So the force equals Gmm over r squared. That's 6.67 times 10 to the minus 11. What's the mass of the Earth?
5.97 times 10 power 24.
Power.
24.
And the mass of the Moon?
7.34 times 10 to the 22.
And the distance between them?
385,000 kilometers. But we're supposed to count it from your course, right?
Count what?
From the center of the Earth and from the center of the Moon.
Yeah, I didn't make it clear here, but that's what I meant.
Okay.
Distance between the centers. Okay, calculate that, please. Will it be a big number or a small number? I think the Earth will have a good force with the Moon. Should be big. Yep.
1.97 multiplied with 10 to the power 20.
Great. Continue. Continue. Yep. So the next one is then. Oh, dudes.
Oh, wait,
All right. The next one. How long does it take the Moon to orbit the Earth? So what type of problem is this? Circular. Yeah?
Yes.
Okay, let's do this one together. No, it's the same information, it's just this time now. Okay, dokie. Yeah? No. Yeah? Okay. Now, we want the time this time. So, here is the Moon, here is the Earth, and it's moving around in a circle. So what's the force if it's moving in a circle? You have two choices. You can say m omega squared, or you can say m, what's the other formula? V squared over r. Which one should we use here if we want the time?
The first one.
Yeah, the first one. Because we can get the omega.
But for that also we can, right? We can use the UV ATS.
We'll use this one. So then omega equals f over m or square root. And yes, you're right, Amanda. What does omega equal also? 2 pi over t equals root f over m or. So what does t equal? 2 pi root m r over f. This is an example. Do we know 2? Yes. Do we know pi? Yes. Do we know the mass of the moon? Yes. Do we know the distance, the radius between the moon and the earth? Yes. Do we know the force between the earth and the moon? Yes.
No.
Here it is here.
What is R?
This is or, the distance. The radius of the circle, the distance between them. Okay, so can you calculate the time here, please?
What is the force?
The last answer. The answer you gave me.
The R is 385,000.
Yep.
The mass is the mass of the moon.
Yes. This is the one that is moving. Okay, say that again.
2379716.
This is in seconds. Can you change this into days?
Divided by 3,000.
And then 24.
Okay.
For hours, and then days.
And then about 24. 24, 1.5 days.
About 28 days. Think. Does that make sense? The moon takes 28 days to go around the Earth? It does. Doesn't it? It takes about 1 month for the moon to go around the Earth. So this is the answer we expected. Yep. Okay. Last question here. Write this down. Satellite. Do you know this word? Grace, do you know satellite?
No.
Sophie? Irene? Andy? That's one meaning, yeah. But usually we mean satellite. I'll draw it. So who's this for? Grace and Amanda. So here is the Earth, and a satellite is
Oh,
in space, travels around the Earth. Maybe it sends your TV signal down. Yeah, this is a satellite. Which country had the first satellite? Oh no. Russia, yeah. Do you learn this in China? Or South Korea? Which country had the first satellite? Russia, yeah. You not learn this in middle school?
I don't care about it.
No?
In Chinese.
Yeah, but you know Russia.
Yeah.
Yeah, yeah.
Country I know.
Yes, yes, yeah. In some,
People are powerful.
they think they're very powerful.
Beijing.
South Korean students, do you learn this in middle school?
Maybe universal.
Maybe, okay, okay. So nobody knows the name of the first satellite, no?
We learn for
Sputnik.
Oh yeah.
You know this?
Yeah.
Sputnik?
Familiar.
Yeah.
Yeah, I
Okay.
have read it.
Okay. Right, let's have a look at this one. Can we do it now? So, well, actually, here's my picture here.
Is Sputnik still somewhere?
Oh, goodness, no.
Yeah.
It would be like 60 years old. No, maybe. Yeah, 60 years old. Right, so the potential energy of the satellite is equal to minus GMM over R. Now, do we know the G? Yes. Do we know the mass of the Earth? Yes. Do we know the mass of the satellite? Yes. And just be careful, the radius is actually R plus H. It's the Earth and the satellite's height. Can you type the numbers in? Tell me what you get. So you need G, mass of the Earth, mass of the satellite, radius of the Earth, and height of the satellite. Tell me what you got.
G is
6.67, 10 minus 11.
Can we use the G omega?
I think it's the same, but I'm not sure.
big and Earth.
Yep.
Yeah, it's the same.
More and
Mass of satellite,
let's leave it.
100, I think. Okay.
Get better.
Now twist yourself.
Minus 9.44 multiplied 10 to the power of 52.
Whoa. This big, are you sure?
I'm not sure. So I'm thinking hard.
I got minus 945168100.
10 to the...
No.
10 0 1 2 3 4 5 6 7 8.
Minus 9 point...
4 5.
10 to the...
Minus 8.
Minus 8.
I mean 8, sorry.
8, okay.
G is E.
G is E?
No.
G is 6.67 times 10 to the minus 11.
Oh, minus 11.
Yes.
No.
Gimme, let me see what you typed in. Yeah. Ah, great. Kilometers.
Oh.
Yes. What? Hareen, what did you say you got?
9.45 times 10 to the power of 8.
9. I got 4.
I might have made a mistake.
You didn't square, did you? You're not supposed to square.
No, I didn't. 9.49.
Right, maybe it's my mistake. Yeah, sorry, Hareen, I got minus for 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9 joules.
Right. I don't think I get it.
Oh. Let me just change this G to I need to bring my calculator.
-9.
Oh, sorry, my mistake again. I don't know. Bring me your calculator. What am I typing in differently? Come up, come up. -6.67. Yeah, -6.67 times 10 to the -11 times 5.97 times 10 power 24 times 100, yeah, over 6371000 plus 3578600. Oh, another O. Yes. Okay. Thank you, Hareen.
Yeah.
Right, so that's the answer there for that one. So that's roughly -1 gigajoule. Roughly. Okay. 10 to the 8 here. Oh, I said roughly, yeah. If you want to do it more accurately, mega. Oh, yeah, 10 to the 9, yeah. Or more accurately, -945. No, I'll just leave it like this. Joules. Okay.
Wow. Steven.
What?
Dear Steven.
What?
Look at this.
Well, it's great.
No.
Added.
You hate me.
I don't hate you. This is because I care about everybody. Okay, you got this? Yeah? Okay. I guess we have to finish there. So there are, in this lesson, one more topic, and then we're into the final section of the course, which is the atom. So there's 9 topics in that. And then once the atom is finished, then we will do exam papers in class. Okay? But can we have 2 hours tomorrow?
Yeah.
Why not?
Okay.
Oh, we don't have them on Wednesdays. Thursday.
12 hours.
We'll try to finish fields on Thursday. Yeah. And then next week we'll start atoms, and that will take about 2 or 3 weeks. And then we'll have about 2 weeks for exam papers. Yeah, I think there's 5 weeks left, isn't there? Yeah, so that's okay. Right, so also don't forget for Monday to bring your laptop. Isn't that what I said for Monday? Didn't I say Monday? Anyways, Has everybody got the lab journal finished?
Yeah, check my.
No, I don't want to check it now. I want to check your lab journal on Thursday, and then on Monday I want to look at your type reports on your laptop.
But I have a question.
Okay, you can ask me.